Hi, my name is Thijs.
And I'm Marianna.
And this three-part video series is all about the Massive Storage Engine version 3. In the first part, Ariana and I will explain what the Massive Storage Engine, or MSE as we'll call it, is, why you should use it, how it works, and how you can benefit from its improved LRU memory eviction mechanism. The Massive Storage Engine is a so-called stevedore that ships with Varnish Enterprise. A stevedore is a component that is responsible for storing objects in cache, keeping track of metadata, handling hot datasets, and object eviction when either the cache is full or when items from the cache are forcefully purged. For those who don't know, Varnish Enterprise is the leading caching and HTTP acceleration solution that optimizes performance and scalability of websites, APIs, content delivery, and video streaming. MSE version 3, or Massive Storage Engine version 3, is a best of both worlds solution that combines the raw speed and performance of memory and the reliability of disk, delivering content at high performance and yet providing persistence for large datasets. So why would you use it? Why would you use MSE 3, or Massive Storage Engine version 3 as we'll refer to it? MSE 3 was designed from the ground up to solve content storage and content delivery challenges for businesses with large volumes of data, and tackling certain limitations that exist both in the file and memory stevedores that also come with Varnish. Whereas the standard memory stevedore only focuses on performance, it's therefore not particularly good at handling large volumes of data, and there's also some cache eviction limitations. On the other hand, the file stevedore is optimized for handling large volumes of data, but it's not particularly fast, can introduce disk fragmentation, and does not offer persistence, surprisingly. Therefore, MSE 3 is the perfect match for video streaming and content delivery. But nevertheless, even if your datasets aren't that large, you can still use MSE 3 as a memory-only cache and benefit from its improved cache eviction mechanisms.
MSE comes with a configuration file, which defines how objects should be stored in cache. In this configuration file, we are going to define an environment which comes with an ID and a memory cache size, which in this case is 100 GB. If we were to start Varnish using this configuration file, we would have a memory-only setup, which means it will be non-persistent, but still it will outperform the regular Varnish stevedore because of how objects are stored in cache and because we have an improved LRU eviction algorithm.
So how does this improved LRU eviction mechanism work? It's relatively simple. When the cache is full, Varnish will evict the least recently used object from cache to free up space in memory and to be able to store new objects in there. This is what we call LRU, least recently used. But the standard memory implementation of Varnish is prone to so-called LRU eviction race conditions, meaning that on high concurrency architectures, threads that try to free up space to store new objects in the cache can't always use that space, because competing threads that are also looking for free space might steal the freshly allocated memory to store their own objects. When this happens, the original thread will retry until it succeeds, but as a consequence might end up in a loop state. When the configurable so-called nuke limit is reached, Varnish will stop, fail, and return an HTTP 503 error. And that is something we must avoid. MSE, on the other hand, is not subject to these LRU eviction race conditions, because the improved LRU eviction mechanism was designed in such a way that concurrent requests don't compete with each other. And this happens by introducing a level of isolation. Additionally, the standard Varnish backend request coalescing assures that multiple fetches for the same object are put on a waiting list and are fulfilled with one single backend request. This makes sure that duplicate content doesn't get stored in the cache as a potential side effect from this isolation, and it also reduces the number of backend requests. Thanks for watching part 1. There's still 2 more parts in this series, and if you click the link at the right upper hand corner, you'll skip immediately to episode 2, in which we'll talk about cache persistence, content distribution, and how the persistence layer can serve as a secondary origin.